Well, pre-calculus classes, as always, good morning, good afternoon, or good evening. We are going to finish up section 2.4 here today. We'll talk a little bit more about what synthetic division actually represents here. And one of the things that certainly as you work through things on Pearson that you will see them refer to is the remainder theorem. And basically what that is saying is that if a polynomial is divided by some divisor x minus k, the remainder will be f of k. And so that's something we're going to actually look at, two ways to show you one other thing other than just factoring that either synthetic or long division represents. Well, if you're asked to use the remainder theorem to evaluate the following function at x equals -3, well, certainly up until now, if you would have seen f of -3, well, what does that mean we do? That means we plug -3 in for x. And when you do that, I know that's -27 times 3 is -81. 9 times 8 is 72. -15 and -7. So you get -31. Now, another way to look at this is instead of just plugging in that value to evaluate it, we can use -3 and do synthetic division. So bring down the 3, multiply, add, multiply, add, multiply, and add. Well, you can see your remainder matches what you get when you plug that in to evaluate. So again, one of the reasons I actually prefer this in a way, because for one thing, you know, the numbers are a lot smaller. You know, here the biggest number I ever had was a -31. Here you had -81, +72, adding a whole bunch of things up. The other reason why this is actually very useful is a lot of the time we actually care less about the remainder and more about these remaining numbers, and you don't get those remaining numbers if you just plug in the -3. So synthetic division, long division, is also a way of technically evaluating a function. Usually what we're evaluating it for is the value 0. So there is one thing that comes up with synthetic division. A couple of other things that we'll talk about here, and then finish up with one final example. The second half of 2.4, the notes are actually a lot shorter than the first half were. Now, the remainder tells us several things. You know, r gives the value of the function at x equals k, or f of k equals r. That's what we just kind of talked about with example 6 there. If the remainder is 0, x minus k is a factor of f of k. That is what we talked about in the final examples from 2.4 day 1. As an example, you know, here our remainder was 0. This was example 4. That's what that's saying. And then if the remainder is 0, k comma 0 is an x-intercept of the graph at f. So again, just kind of a few different things that you do get from the remainder. So one last example here. Use the remainder theorem to show that x minus 2 and x plus 3 are factors of 2x plus 4 plus 7x to the third minus 4x squared minus 27x minus 18. I suppose if you really truly wanted, you could do this with long division. I really hope that is not the choice you make. Basically, what we're going to do is we're going to pick one of these to start. You know, whether we use the x minus 2, x plus 3. If I use the x minus 2, I'm going to use 2 for my synthetic division. And then I'm going to put the 2, the 7, the -4, the -27, and the -18. One thing that you'll notice, there is a reason I am definitely not just plugging 2 in. And that is now when we do our synthetic division. So bring down the 2, 2 times 2 is 4, add 11, 11 times 2 is 22, 18 times 2 is 36. We add there, you get 9, positive 18. Our remainder is in fact 0. Now, so it says use the remainder theorem to show that x minus 2 and x plus 3 are factors. Well, we've shown that x minus 2 is. Now, from here, what we can do is when we do synthetic division for the x plus 3, we can now use these remaining numbers, and you actually eliminate a step. So if it's x plus 3, I'm going to use negative 3. Again, so we'll bring the 2 down. 2 times negative 3 is negative 6. 5, negative 15, 3, and negative 9, again, gives us a remainder of 0. So, we have also now shown that x plus 3 works. Now, one of the other reasons why you don't want to just plug 2 in, plug negative 3 in. With what's left, 2x squared plus 5x plus 3. We can now factor this fully. You are not able to get the full factorization if you just plug numbers in, which is what we'll truly be working towards as we get into section 2.5 in the next half of the chapter. So if you take, again, what multiplies to 6 adds to 5, well, 2 and 3, so I can split the middle. 2x squared, 2x, 3x, and 3, and then you can factor by grouping. So take out a 2x, take out a 3, and there is your full factorization. Technically, you could even, if you wanted, bring down the x plus 3 and the x minus 2. So these are the 4 factors of what we started with up there. So again, that kind of really talks through just about everything that synthetic division and long division represent.